Tonight, we're going to explore a question that sounds like it should have a simple answer, but turns out to be one of the deepest, most unsettling, most consequential questions in all of science. What exists outside the observable universe? Not what might exist, not what could theoretically exist. What does physics, the actual equations, the actual data, the actual measurements we have made with the most sensitive instruments ever built, tell us is out there beyond the edge of what we can see? Here is the problem. The answer is not nothing, and it is not something we fully understand, and the implications of the most likely answers range from mildly surprising to the complete dissolution of the idea that the universe we can observe is anything other than an infinitesimally small corner of a structure so vast that the word vast stops being useful. There is a boundary around us, not a physical wall, not a region of space that is different from the space we inhabit, simply the limit of how far light has had time to travel since the universe began. Everything within that boundary is the observable universe. Everything beyond it is, by definition, unobservable to us. Not in principle, not with better telescopes, not with future technology, permanently, absolutely, irreversibly beyond any possible observation. But unobservable does not mean non-existent. And when you examine what physics tells us about what must be out there, when you follow the equations to their conclusions and listen to what the data is saying, you discover something extraordinary. The universe almost certainly does not end at our horizon. It almost certainly continues, and it almost certainly continues for a very long time, possibly forever, possibly containing within it things so strange, so different from anything in our observable patch, that our entire history of cosmic exploration has not equipped us with the concepts needed to fully describe them. 7 things that physics tells us about what exists beyond the edge of the observable universe. Some confirmed, some strongly implied, some deeply speculative but mathematically serious, all of them profound. By the end of tonight, you're going to understand exactly what that boundary is, why it exists, what we can and cannot know about what lies beyond it, and what the most serious answers to this question imply about the nature of reality itself. Before we begin, if these questions about the structure of everything pull at you the way they pull at us, like or subscribe. It costs you nothing and helps us reach more minds that want to think about things like this. Now, let's begin. The year is 1929. An astronomer named Edwin Hubble is sitting with data from a series of careful measurements of distant galaxies. He has been measuring their spectra, the pattern of light they emit, and he has noticed something that no one has adequately explained. Almost every galaxy he can observe is moving away from us. Not just moving in a very specific way. The farther away a galaxy is, the faster it is receding, not by a little, proportionally. A galaxy twice as far away is receding at twice the speed. A galaxy 10 times as far away is receding at 10 times the speed. Hubble does not fully understand what this means. He has measured a relationship, what we now call the Hubble constant, between distance and recession velocity. He has found that the universe is expanding, not that galaxies are flying through space away from a central point, like shrapnel from an explosion. Something stranger. Space itself is expanding. Every region of space is getting larger. Every pair of unbound objects in the universe is getting farther apart. Not because they are moving through space, but because the space between them is growing. If the universe is expanding now, it was smaller in the past. Trace the expansion backward and the universe converges on a point of almost unimaginable density and temperature. A beginning, the Big Bang. And if there was a beginning, there is a limit to how far light could have traveled since then. Light moves at a finite speed. The universe has a finite age. Multiply the two and you get a maximum distance that any photon could have covered since the universe became transparent enough for photons to travel freely. That distance defines the observable universe. Currently, the observable universe has a radius of about 46 billion light years, not 13.8 billion light years, which would be the naive calculation of the speed of light times the age of the universe. 46 billion, because the space through which those ancient photons traveled has itself been expanding for 13.8 billion years, stretching the distances. Everything within 46 billion light years of us we can in principle observe. Everything beyond that we cannot. Not today, not with better telescopes, not ever, because the photons from those regions simply have not had time to reach us. They are on their way, but they will never arrive because the space they are trying to cross is expanding faster than they can traverse it. This is the boundary. This is the edge of the observable universe. And now the question is, what lies beyond it? The first thing beyond the horizon, more of the same. The most conservative, most defensible, most observationally grounded answer to what lies beyond our horizon is this: more universe, similar to what we have here. More galaxies, more stars, more planets, more cosmic structure, more of the same laws of physics producing the same range of phenomena we observe within our observable bubble. This sounds unexciting until you examine the evidence for it and think about the implications. The universe we can observe is remarkably uniform on the largest scales. When we average over regions larger than about 1 billion light years, the universe looks the same in every direction. The density of matter and energy is the same. The distribution of galaxies is similar. The cosmic microwave background, the oldest light we can detect, arriving from the edge of our observable bubble, shows temperature variations of only 1 part in 100,000. The universe is extraordinarily smooth. This smoothness is a clue about what lies beyond. If the universe were dramatically different just beyond our horizon, if there were a wall of void or a wall of extreme density just outside our observable sphere, you would expect some sign of it visible at the edge of what we can see. The fact that the edge looks just as smooth and uniform as the rest suggests the universe continues beyond it in much the same fashion. Inflation, the extraordinarily rapid expansion thought to have occurred in the universe's first tiny fraction of a second, provides the theoretical explanation for this smoothness. Before inflation, a tiny patch of the primordial universe inflated to a size enormously larger than our current observable sphere. The smoothness of our observable universe is a consequence of that inflation, and inflation implies that the total inflated region is many times larger than what we can observe. The universe beyond our horizon is a continuation of the inflated patch, with the same initial conditions, the same laws of physics, the same basic structure. The simplest inflation models suggest the total universe is at least 10 to the 23rd times larger than our observable sphere. Some models suggest factors far larger still. The universe beyond our horizon, in the most conservative reading of the physics, is simply more of what we already know. More galaxies, more stars, more planets, more cosmic history, but more is not the same as identical. And here is where the first genuinely surprising implication appears. Before we explore what is out there, we need to be precise about what the boundary actually is. The observable universe is not a physical thing. It is not a wall or a surface or a region with different properties. It is a horizon, like the visual horizon you see when you look out to sea. The ocean does not end at your horizon. Your ability to see the ocean ends there. The water beyond is real. The ships beyond it are real. They are simply beyond the range of your direct observation. The cosmic horizon is similar. The space beyond 46 billion light years from us is real space. The galaxies there, if any exist, are real galaxies. The physical laws governing them are, as far as we know, identical to the physical laws governing us. There is nothing special about the boundary from the perspective of anyone or anything on the other side of it. If someone is living in a galaxy 60 billion light years from us, they have their own observable universe centered on themselves, and we are beyond their horizon, just as they are beyond our. This is a crucial point. The observable universe is defined by our location and the age of the universe. It is observer dependent. Every point in space has its own observable universe, its own horizon, its own sphere of visibility. The universe itself, the total structure of space-time and its contents, is a different thing. It could be vastly larger than any single observer's horizon sphere, or it could be infinite, or it could have a specific finite size. These are different possibilities, and physics addresses them differently. What we are asking tonight is, what does physics tell us about the total universe? The universe beyond anyone's horizon, the universe in its full extent, and the answer comes in layers, each one more surprising than the last. A universe that is many times larger than our observable sphere, governed by the same physical laws, beginning with essentially the same initial conditions, will eventually, in regions far enough from our own, produce the same configurations of matter that it has produced here. There are a finite number of ways to arrange the particles within a volume the size of our observable universe. The number is not small. It is approximately 10 to the power of 10 to the power of 122, a number so incomprehensibly large that it makes a Google look microscopic. But if the universe is large enough, regions separated by enormous distances will eventually, by probability alone, replicate any given configuration, including configurations indistinguishable from our observable universe, including, within those, regions indistinguishable from the Milky Way, indistinguishable from the solar system, indistinguishable from Earth, and inhabited by beings indistinguishable from us. The distance to the nearest such region where all the particles in our observable universe are arranged in essentially the same way is estimated at 10 to the power of 10 to the power of 122 meters, a number that has no name and cannot be meaningfully visualized. But if the universe is truly large enough, that distance is finite. The copies exist. This is not mysticism. This is straightforward probability applied to a sufficiently large but finite set of particle configurations within a sufficiently large universe. The physicist Max Tegmark has called this the Level 1 multiverse. Though it is not a multiverse in any exotic sense, it is simply a universe large enough for statistical repetition. The idea is uncomfortable because it challenges our intuitive sense of uniqueness. We feel singular, our histories feel unique, our choices feel unrepeated. But in a universe of sufficient size, the laws of statistics do not care about our feelings. Given enough volume and enough particle configurations, repetition is not just possible, it is inevitable. The second thing beyond the horizon, different initial conditions. This is where we move from the conservative to the genuinely strange. Inflation, the rapid early expansion that explains the smoothness and flatness and horizon uniformity of our observable universe, does not necessarily produce a uniform infinite universe. Many inflation models predict that inflation does not end everywhere at the same time. Different regions of the inflating space end their inflationary period at different moments. When inflation ends in a region, that region settles into a hot, dense state and begins the conventional Big Bang evolution we observe in our own universe. But the regions that have not yet ended inflation continue inflating, and because they are inflating, they expand faster than the speed of light and become causally disconnected from the regions that have already ended inflation. They are beyond each other's horizons permanently. This process, called eternal inflation, produces what physicists call a multiverse of bubble universes. Each bubble is a region where inflation ended and a conventional universe evolved. Our observable universe is one bubble. There are others. countless others, perhaps an infinite number, being constantly produced as inflation ends in different patches of the eternally inflating space. Here is the critical point. When inflation ends in a region, the specific way it ends determines the physical constants of the universe that forms there, the strength of gravity, the mass of the electron, the cosmological constant that determines how fast the universe expands, the number of spatial dimensions. These parameters are not necessarily the same in every bubble. They depend on how inflation ended, on the specific path through the quantum field landscape that the region took when it settled into its final state. If eternal inflation is correct, the bubbles beyond our horizon are not just more of the same universe. They are different universes with different physical laws, different constants, different structure. Some of them may be hostile to any form of complexity. Others may be similar to ours, but with slightly different constants that produce stars of different sizes or chemistry of different richness. A very few may be finely tuned for complexity in ways that differ from our own universe, but still permit extraordinary structure. This is the Level 2 Multiverse, as Tegmark calls it. Not just more universe with the same laws, but a landscape of universes with varying laws, separated by inflationary regions that will never permit communication between them. The troubling implication is this: if physical constants can vary between bubble universes, and our bubble has the specific constants it has, then we need to explain why our constants are what they are. One answer is the anthropic principle. We observe the constants we observe because only certain constants permit observers. The constants have to be compatible with our existence for us to exist, to measure them. In a multiverse with many different sets of constants, we should not be surprised to find ourselves in a bubble with constants that permit our existence. That is the only kind of bubble we could find ourselves in. This reasoning is either profound or circular, depending on who you ask. The debate in the physics community about the anthropic principle and what explanatory weight it carries is genuine and unresolved. But the physics of eternal inflation that motivates the question is taken seriously by many of the most careful cosmologists working today. The third thing beyond the horizon, the inflationary landscape. The string theory landscape is, depending on your perspective, either the most important idea in fundamental physics or the most dangerous idea in fundamental physics. String theory, the leading candidate for a theory that unifies quantum mechanics and general relativity, predicts a vast number of possible vacuum states. Different ways the extra dimensions of string theory can be compactified, curled up into configurations too small to observe. Each compactification produces a different set of effective four-dimensional physical constants, different particle masses, different force strengths, different cosmological constants. The number of possible compactifications is estimated to be around 10 to the 500, a number that makes the number of atoms in the observable universe look negligible. If each of these vacuum states can be realized in a bubble universe created by eternal inflation, then the space of possible universes is not just large, it is comprehensive. It contains universes with every physically consistent combinations of parameters that string theory permits. Universes where gravity is 10 times stronger, universes where the electron is heavier than the proton, universes where the cosmological constant is large and positive and the universe expanded too fast for any structure to form. Universes where the cosmological constant is large and negative and the universe recollapsed within microseconds. Universes with different numbers of effective large spatial dimensions. Most of these universes are barren. They do not permit atoms or star or chemistry or anything that could be called complexity. A tiny fraction permit the conditions for structure, an even tinier fraction permit conditions resembling ours. But if the landscape is real and the multiverse is real, the question of why our universe has its specific constants becomes not a question about fine-tuning requiring explanation, but a statistical question about which universes in the landscape permit observers. The answer is that almost none of them do, and we find ourselves in one of the rare exceptions because we could not exist in any of the others. This is either a profound insight into the nature of physical law or an abandonment of the project of physics. Critics argue that a theory that explains our constants by appealing to other unobservable universes with different constants is not science. It is metaphysics dressed in mathematical clothing. If we can never observe the other bubbles, if no experiment can ever test whether they exist, then proposing their existence is not a scientific hypothesis in any meaningful sense. Supporters argue that the landscape emerges from string theory, which is itself motivated by the need for mathematical consistency in a unified theory of physics. They argue that the inability to directly observe something does not make it non-scientific. We cannot directly observe the interiors of black holes, the first moments of the Big Bang, or the quantum states of individual particles being measured. Indirect evidence and mathematical consistency are legitimate tools of science. This debate is ongoing. The landscape and the string theory multiverse are serious proposals by serious physicists. They are not settled. They may never be settled, but they represent our current best attempt to understand what lies beyond the horizon, not just in space, but in the deeper sense of what determines why our physical laws are what they are. Let us step back from the theoretical for a moment and think about what we actually know from data. The observable universe contains roughly 2 trillion galaxies, a number revised upward significantly in 2016 from the previous estimate of 200 billion. Each galaxy contains billions to hundreds of billions of stars. Our galaxy alone contains an estimated 300 billion stars, many of which have planetary systems. The observable universe contains more stars than there are grains of sand on every beach and desert on Earth. This is the universe we can see, and it occupies, on the most conservative inflation models, a tiny fraction of 1% of the total universe. The galaxy count outside our horizon dwarfs what we can observe by a factor that has no meaningful name: the cosmic microwave background, which we can map in extraordinary detail, shows the universe at 380,000 years after the Big Bang, as seen from every direction. The fluctuations in that map, tiny temperature variations of 1 part in 100,000, are the seeds of all the structure we observe today. Those fluctuations were generated by quantum processes during inflation, stretched to cosmic scales by the rapid expansion. Crucially, the pattern of those fluctuations extends to the largest angular scales we can measure. And at those largest scales, the pattern does not obviously cut off. The fluctuations at the edge of our observable sphere look similar to the fluctuations at smaller scales. There is no sharp boundary visible in the data. The universe beyond our horizon, in this observational sense, appears to be a continuation of the one we can see. This is not proof that the universe continues beyond our horizon in the way we expect. It is consistent with it. And in science, consistency with observations is the evidentiary standard we work with when direct observation is unavailable. The universe beyond the horizon is real. The physics says so. The data is consistent with it. The question is the nature of that reality. And on that question, the physics gives us a range of answers from conservative to extraordinary. The fourth thing beyond the horizon: the topology of everything. Here is a question that sounds mathematical but is deeply physical. What is the shape of the universe? Not the shape of the observable universe, the shape of everything, the total topological structure of space. The universe could be flat, in the geometric sense of the word, meaning that parallel lines never meet, that the angles of a triangle add up to exactly 180 degrees, that the geometry of space on large scales is Euclidean. Measurements of the cosmic microwave background suggest the universe is flat to within about 0.5%. It is very nearly flat. If the universe is flat and infinite, it has no edges, no boundaries, no center, and extends forever in every direction. What lies beyond our horizon is more flat, infinite universe. But the universe being flat does not mean it has to be infinite. A flat universe can have a topology that makes it finite. The simplest example is a three-dimensional torus. Imagine a three-dimensional box where the left wall connects to the right wall, the top wall connects to the bottom wall, and the front wall connects to the back wall. Space in such a universe is flat. Geometry works normally, but if you travel far enough in any direction, you come back to where you started. In a toroidal universe, what lies beyond our horizon in any direction is, potentially, the same universe we already inhabit, seen from a different angle. Possibly, our own galaxy is out there, billions of light years away in every direction, appearing to us as a distant foreign galaxy, because the light has taken billions of years to go around the loop and come back. Physicists have searched for this signal. If the universe is a torus smaller than our observable sphere, we should see matched patterns in the cosmic microwave background. Specific spots that have the same temperature and polarization pattern in opposite directions on the sky, because they are actually the same physical region seen from two different angles around the loop. The searchers have found no convincing evidence of such matching patterns. The universe, if it is toroidal, is larger than our observable sphere. Its topology is hidden beyond our horizon. The universe could also be spherical, positively curved, like the surface of a sphere, but in 3 dimensions. In such a universe, parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees, and the universe is finite. Travel far enough in any direction and you return to your starting point. But a spherical universe slightly larger than our observable sphere would be essentially indistinguishable from a flat, infinite universe, given our current measurement precision. The curvature would be too gentle to detect. The shape of the universe beyond our horizon is genuinely unknown. It could be infinite and flat. It could be finite and toroidal. It could be finite and spherical. It could have an exotic topology involving handles or holes or more complex structures that have no simple visual analogy. Physics does not currently have the data to discriminate between these possibilities. What lies beyond the horizon depends partly on which of these is true. In an infinite flat universe, what lies beyond is infinite more space. In a finite toroidal universe, what lies beyond is the universe looping back on itself. These are fundamentally different answers to the question, and we do not know which is correct. The fifth thing beyond the horizon. Regions of different fate. The expansion of the universe is accelerating. We know this from observations of distant supernovas, from the pattern of the cosmic microwave background, from the large-scale structure of the galaxy distribution. Something which we call dark energy is pushing space apart at an increasing rate. If dark energy remains constant, as the simplest models predict, the universe's expansion will accelerate forever. As it accelerates, more and more of the universe crosses our cosmic event horizon. Galaxies that are currently visible will eventually recede beyond our horizon, and their light will never reach us again. The observable universe will shrink, not grow, as time passes. More and more of existence becomes permanently invisible, but dark energy might not remain constant. It might change over time, and depending on how it changes, the fate of the universe beyond our horizon could be very different. If dark energy grows stronger over time, the expansion could eventually become so extreme that it tears apart bound structures. Galaxies are currently bound by gravity against the expansion. Galaxy clusters are bound. Even individual galaxies are held together by gravity stronger than the current expansion force. But if dark energy grows without bound, a scenario called the Big Rip, the expansion force eventually exceeds the gravitational binding of galaxy clusters, then individual galaxies, then stellar systems, then planets, then molecules, then atoms, until the universe is torn apart at every scale. The Big Rip would be the literal dissolution of all structure. If dark energy weakens over time or reverses, becoming attractive rather than repulsive, the expansion could slow, stop, and reverse. The universe could begin contracting toward a big crunch, a collapse that mirrors the Big Bang in reverse. Everything converges. Temperatures and densities increase without bound. If dark energy fluctuates, or if the underlying quantum vacuum is metastable, the universe could undergo a phase transition. A bubble of true vacuum could nucleate somewhere in the cosmos and expand outward at the speed of light. Inside the bubble, the laws of physics would be different. Not slightly different, fundamentally different, because the vacuum state that determines physical constants would have changed. The bubble would sweep across the universe, and everything it encountered would be converted into a region where the physics we know no longer applies. This vacuum decay scenario is genuinely considered by physicists. The Higgs field, whose discovery was confirmed in 2012, appears to have a value that puts the universe in a potentially metastable state. The calculations are uncertain. The universe might be stable. It might be metastable, meaning the decay could happen but requires a very unlikely quantum fluctuation. The probability per unit volume per unit time is extraordinarily small. But in a universe of sufficient size and age, small probabilities multiply. What lies beyond our horizon might include regions of different fate, regions destined for a big rip or approaching a big crunch, or already swept through by a vacuum decay bubble moving toward us at the speed of light. We would not be able to see any of these coming before they arrived. The first warning would also be the last experience. The instruments we have built to examine the edge of the observable universe are extraordinary. The James Webb Space Telescope, launched in December 2021, observes the universe in infrared light with a sensitivity and resolution that dwarfs its predecessors. It can detect galaxies that formed within a few 100 million years of the Big Bang. It sees the universe as it was 13.4 billion years ago. It is looking at a universe barely older than an infant, when the first stars and galaxies were just beginning to assemble. The data from Webb has already produced surprises. Early galaxies appear to be more massive, more numerous, more chemically enriched than models predicted. Something about early galaxy formation is not yet fully understood. The universe at its youngest observable moments is not behaving quite the way we expected. This matters for the question of what lies beyond the horizon, because our models of what is out there are only as reliable as our models of what we can see. If early galaxy formation is not fully understood, our extrapolation of what the same processes would produce in regions we cannot see is uncertain. But the observations also confirm the broad picture. The universe was hot and dense at early times. It has been expanding and cooling ever since. The cosmic microwave background is real and matches predictions with extraordinary precision. The large-scale structure of the universe, the web of filaments and voids and galaxy clusters, matches what simulations predict from the initial conditions revealed by the CMB. The universe we can observe behaves at the largest scales in a way that is consistent with our best physical models. And those models, extrapolated beyond our horizon, tell us the universe continues. The same initial conditions, the same physical laws, the same expansion history, the same cosmic web of structure. More of everything we see on scales we cannot observe. The sixth thing beyond the horizon, the quantum landscape of all possible histories. Here we reach the most philosophically challenging territory. Quantum mechanics, the theory that governs the behavior of matter and energy at the smallest scales, has an interpretation problem. It tells us with extraordinary precision what the probability of any given measurement outcome is. It does not tell us which of the possible outcomes actually happens. The wave function, the mathematical object that encodes all the quantum possibilities of a system, evolves deterministically according to the Schrödinger equation. But when a measurement is made, a specific outcome occurs, and the wave function appears to collapse to a single value. What happens to the other possibilities? The Copenhagen interpretation, the standard textbook answer, says nothing. The other possibilities were never real. Only the measured outcome is real. The wave function was a calculating device, not a physical object. But there is another interpretation. The many worlds interpretation, developed by Hugh Everett in 1957, says something very different. The wave function never collapses. All the possibilities continue to evolve. What looks like a collapse, what looks like a single outcome being selected, is actually the universe splitting into branches, one for each possible outcome. Every quantum measurement that has ever been made has branched the universe into as many copies as there were possible outcomes. In the many worlds interpretation, all possible outcomes of all quantum measurements are real. They are happening right now in branches of reality that have become causally disconnected from each other. The branching happens everywhere, constantly, at every scale, for every quantum event. The number of branches is incomprehensible. The total structure is a quantum multiverse containing, in some sense, all possible histories of the universe. These branches are not located somewhere in space beyond our horizon. They exist in the same space we do, in the same region, right here. But they are orthogonal in the mathematical sense. They share the same spatial location, but differ in their quantum states. They cannot interact with each other and cannot be observed from within any single branch. Is the many worlds interpretation correct? The physics community is divided. It is empirically equivalent to Copenhagen at the level of predictions. No experiment currently known can distinguish between them. The disagreement is about interpretation, about what kind of thing the ontology, about what kind of thing the wave function is. These are profound questions, and they do not yet have agreed answers. But if many worlds is correct, what exists beyond the observable universe includes, in the most expansive sense, every possible quantum history of the cosmos. Every path not taken, every measurement outcome not observed, every particle that could have gone left but went right. The universe is not just large in spatial extent. It is large in possibility space, and every possibility is equally real. The cumulative picture these 7 answers paint is extraordinary. Beyond the 46 billion light-year bubble we can observe is more universe, probably much more, following the same physical laws we know. Then possibly bubble universes with different physical constants, products of eternal inflation. Then possibly the full landscape of string theory vacua, each realized in its own bubble. Then possibly a universe with a topology that loops back on itself. Then possibly regions of different cosmic fate, heading toward different ends. Then possibly the branching quantum multiverse of all possible histories. Then possibly the totality of all mathematical structures. These answers are not mutually exclusive. Several of them could be simultaneously correct. The level 1 multiverse, more universe with the same laws, is almost certainly true if inflation is true. The level 2 multiverse from eternal inflation is a serious possibility taken seriously by serious cosmologists. The level 3 many worlds quantum multiverse follows from a specific interpretation of quantum mechanics that is empirically consistent with all data. The level 4 mathematical multiverse is the most speculative but represents the endpoint of a particular philosophical trajectory. None of them are confirmed. Some of them may be unconfirmable in principle. And this is the honest situation we are in. The 7th thing beyond the horizon, mathematical reality itself. This is the most extreme position, the one that most clearly crosses the line from physics into philosophy, and yet it is held by serious physicists and mathematicians and is worth understanding on its own terms. Max Tegmark, the physicist we mentioned earlier, has proposed what he calls the mathematical universe hypothesis. It states that physical reality is not just described by mathematics, it is mathematics. Every self-consistent mathematical structure exists as a physical reality somewhere in the totality of existence. If this is correct, then beyond our observable universe, beyond the level 1 multiverse of statistical repetitions, beyond the level 2 multiverse of different physical constants from eternal inflation, beyond the level 3 multiverse of many worlds quantum branches, there is a level 4 structure containing every mathematically possible universe. Universes with different numbers of spatial dimensions, universes governed by different fundamental equations, universes where the concept of time does not exist, universes where causality works differently, universes where the concept of a particle has no analog. Every consistent mathematical framework, every logically possible set of rules is realized as a physical reality in this totality. This is, by any measure, the most expansive answer to what exists beyond the observable universe. It says that everything that is mathematically possible is real. The limitation is not energy or probability or physical law. The limitation is logical consistency. The obvious objection is that this is not science. If every mathematical structure is real, the hypothesis makes no predictions about which one we inhabit that would distinguish it from any other hypothesis. It cannot be tested. It cannot be falsified. Tegmark's response is that the hypothesis does make a prediction. It predicts that we should find ourselves in a universe that can be described by mathematics, and we do. The unreasonable effectiveness of mathematics in describing physical reality, a phrase coined by physicist Eugene Wigner to describe the astonishing fact that abstract mathematics developed with no practical motivation repeatedly turns out to describe the physical world with perfect precision, is itself a prediction of the mathematical universe hypothesis. Whether this argument is compelling or circular or profound is a matter of genuine philosophical debate. But as an answer to what exists beyond the observable universe, it is the most complete possible answer. Everything. Not everything we might naively imagine, not everything we could list, but everything that is logically possible to describe mathematically. There is something important to say about the limits of what we can know. Physics is the project of describing reality using mathematics and testing those descriptions against observations. It has been extraordinarily successful. From the subatomic to the cosmological, from the first microseconds of the Big Bang to the large-scale structure of the universe today, the project of physics has produced descriptions of remarkable precision and scope. But the observable universe is a boundary in a profound sense, not just a practical limitation, an in-principle limitation. No information from beyond 46 billion light-years can reach us. No observation we can make, no instrument we can build, no experiment we can run, can provide direct data about what lies beyond our horizon. This does not mean we know nothing about it. The physical laws we have discovered here should apply there. The initial conditions we have inferred from the cosmic microwave background constrain what the universe looked like beyond our horizon at early times. The mathematics of inflation and string theory and quantum mechanics, derived from studying what we can observe, implies things about what we cannot. These are legitimate inferences, even if they are not direct observations. But there is intellectual honesty required here that is not always present in popular accounts. The multiverse is not confirmed. Eternal inflation is not confirmed. The string theory landscape is not confirmed. These are serious hypotheses with serious mathematical motivation, and they are taken seriously by serious scientists. They are not fringe ideas, but they are not established facts. The honest answer to what exists beyond the observable universe is, we do not know. What physics tells us is a set of possibilities, ranked by plausibility, motivated by different theoretical frameworks, none of them directly testable with current or foreseeable technology. The most conservative possibility, more universe with the same laws, is the best supported. The more exotic possibilities, from eternal inflation to the mathematical multiverse, are speculative but not arbitrary. They follow from taking seriously the physics we already have and extending it beyond where we can observe. The Voyager spacecraft are, right now, in interstellar space. Having crossed the heliopause, the boundary where the sun's influence gives way to the interstellar medium, they are in this space between stars. They are traveling at about 38,000 miles per hour. They are the fastest and most distant objects human beings have ever created. And they are, from the perspective of the observable universe, essentially stationary. The nearest star is 4 light-years away. Voyager would take 73,000 years to reach it. The observable universe is 46 billion light-years in radius. At Voyager's speed, it would take more than a quadrillion years to cross a meaningful fraction of it. We are, in a spatial sense, extraordinarily local creatures. Everything we have ever directly touched, everything any probe we have ever launched has ever reached, is within a few tens of astronomical units of the Sun. A tiny speck in a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, which is itself potentially a tiny bubble in an enormously larger structure. This should be humbling, and it should be exciting, because those 2 trillion galaxies, those hundreds of billions of stars per galaxy, that enormous cosmic web of structure extending to the edge of what we can see, all of it was discovered and mapped and understood by creatures on a small rock orbiting a single star, using instruments built over the last few centuries. We did not need to travel to the edge of the observable universe to know it is there. We did not need to visit distant galaxies to understand them. We built telescopes and detectors and analyzed the light that arrived here and reconstructed the history and structure of an enormous cosmos from a single vantage point. That achievement is remarkable, and it is the foundation on which we base whatever confidence we have about what lies beyond. Here is the deepest version of the question, the one that physics approaches but cannot fully answer. Why is there anything, not what is out there beyond our horizon? Not how large the universe is, but why is there a universe at all? Why is there something rather than nothing? This is not a question physics has answered. Some physicists argue it is not a question physics can answer. Others argue that the multiverse answers it by making the existence of universes a statistical inevitability in a structure large enough to contain all possibilities. If every possible mathematical structure is real, then of course there are universes. Non-existence is not a mathematical structure. Others argue this reasoning is circular. To say that every mathematical structure exists is itself a claim that requires explanation. Why should mathematical possibility entail physical reality? The gap between what can be described mathematically and what actually exists is itself a profound puzzle. These questions push beyond physics into metaphysics, into the philosophy of existence itself. Physics can describe the structure of what exists with extraordinary precision. It cannot, from within its own framework, fully explain why anything exists at all. That question remains open. But what is extraordinary is that a species on a small planet around an ordinary star in an ordinary galaxy has the capacity to ask it. That the universe, in at least one of its observable corners, has produced creatures capable of wondering about the whole of existence, of building instruments sensitive enough to see light from 13 billion years ago, of deriving equations that describe the conditions of the first microseconds of cosmic history, of asking what lies beyond the reach of any possible observation. We are looking at the edge of everything we can ever know. 46 billion light-years in every direction, the most distant light we can ever detect, the oldest signals that will ever reach us, and we are asking what is beyond. The answer is almost certainly more. More universe, more space, more time, more structure, more galaxies and stars and planets, and perhaps more life and perhaps more minds, separated from us by distances so vast that no signal from us will ever reach them, and no signal from them will ever reach us. More existence in more forms than we can enumerate, playing out according to physical laws that may be the same as ours, or may be different. in a total structure that is either enormously large or infinite, or encompasses every possible reality that mathematics can describe. We do not know exactly what is out there. We may never know. The horizon is real and it is permanent, and it seals away most of existence from our direct observation for the entire future of any civilization based in our corner of the cosmos. But the universe is not silent about what lies beyond it. It speaks through the patterns in the microwave background, through the large-scale structure of the galaxy distribution, through the physics of inflation and quantum mechanics and string theory. It gives us mathematical tools that reach further than our instruments. And those tools, applied carefully and honestly, say the same thing in different ways. The observable universe is not the universe. It is a window, a bubble, a horizon-limited sphere of visibility in a structure so much larger that we cannot currently grasp its full extent. And whatever is out there, beyond the reach of any telescope, beyond the reach of any signal we could ever send or receive, it is part of the same reality we inhabit, governed by physics, structured by mathematics. Real in whatever sense anything is real. The universe does not end at our horizon. Our knowledge ends there. The universe continues and continues and continues.